Research Center named Dale Reed, who developed an airplane called the Mini Sniffer, which is what this is, to go up and check on high altitude winds and so forth. And they wanted to keep it up a long time, so hey, let's beam some power up to it, and it won't have to carry so much fuel. It can have an increased payload, more instruments or better instruments and so forth. Also, some thoughts occurred while flying many flights from Burbank Airport up to San Jose. We go to Varian, the high power tubes, get them working and so forth. Gee, could we just have a corridor for the aircraft where we have beamers on the ground, beaming power up to the planes? They can carry less fuel and more people and improve that ratio. All right, now I'm just going to run through some of the events that did happen in wireless power transmission that are in historical quite of interest. Bill Brown with his helicopter, Nobu Kaya with his airship, the first phased array on a mobile platform powering a vehicle. This is Lake Mirabou and his laser blaster, if you will, that ran up a slide wire, lots of thrust. The Marshall Space Flight Center demonstrated the first laser-powered airplane in a hangar out at Edwards Air Force Base. And I think one of the most promising aspects was the Shark program that the Canadians had, where they built this airplane with a rectenna on it and actually flew it for a period of time. It was to be a communications platform. I think indeed the ITU and other elements of harmonics and noise and so forth sort of inhibited the application. But I do think eventually those things will be worked out. Here was a parabola that they used to beam their power up to the Sharp aircraft. And like I say, the phase array from the Japanese over here. And this is a demonstration in 2012 by Jordan Kerr, bless his soul, who's now up there. Did a powering a airplane with a Lockheed, I think, for quite a period of time at 500-meter range and centimeter accuracy of keeping that laser beam on the TV on an airplane. Okay, then along came some ideas from other people to beam power to propulsion vehicles. Kevin Parkin at Caltech did his thesis on millimeter wave power to a rocket. The Japanese used the ITER gyrotron, megawatt at 170 GC. I don't know that they ran it at the full megawatt, but they blasted a rocket off here with it. But wouldn't it be great for SpaceX and others to be able to use a strap-on booster, microwave powered, to assist that fraction of payload that they could put up? So I think that's something I would suggest. And then there's proposed launches from larger aircraft than they do now. Indeed, you could help get those things into the air, like JTOW and RATOW, if you had microwave-powered assistance in getting energy to the vehicle to get off the ground. And it, too, could probably carry a beamer that would beam power to the rocket that it launches and also improve its payload fraction. This is some more of the Escape Dynamics. Was in business for a while, also trying to provide a microwave launched vehicle. Okay, why stepping stones? Can't you just jump out? We know the technology is there. We know the physics is there. Let's get with it and make satellite power systems. Well, we really need to think about safety, develop beam safety standards and system standards. One of the things I'll be talking about is detect, dim, divert, and douse. And those apply to the power beams. The systems are really going to need to be able to detect potential intrusion, or if something is in the beam. I think the worst case somebody told me was the naked skydiver. So you may want to not frisk them. Okay. So similar to airborne collision avoidance, we've got to sense and avoid things that may potentially get into the beam, be they laser or microwave. You've got to avoid those beam collisions. Well, we went through, I won't dwell on this, trying to get a defined service for beam power. We discussed that a good bit. We need to do some more refining of the electromagnetic compatibility techniques. This is for the harmonics and the noise, both from the beamer as well as from the rectenna. Need to improve the beamer and rectenna efficiencies, obviously, and familiarize the citizens, the people out there who are going to pay for this or stand for it, to begin some more benign, I'll call them WPT applications. But one of the key problems that we got to overcome is this one, captured very well by Ted Key. I apologize for the quality of this. Here's the guy in the patent office, got his hand on a button. He pushes the button. This guy flies up. The secretary said, "What's going on?" But the comment down here is transmitting thereby electricity without wires. Now, the best defense is a good offense, and we need somebody to really do the other version of this that shows you we really can do it safely, if you think about it. Now, Howard Bloom is one guy who's really good at putting things out. He should try to develop something in that regard to show that. Okay, this was back in 1978, after the Goldstone demonstrations. I got to thinking about, for the big satellite power system in the sky, what do you do for beam safety? And one of the key elements here was to do sort of a accounting of where all the energy goes. Is it going to the places you want it to go? And obviously with those side lobes, when something is beginning to fly into the beam, there's a great opportunity for a radar to detect, oh, something is scattering energy in the side lobes. Is it going to be a problem? Should we do something about it? But also, you need to be able to run a beam tester. You need to put up little drones like I can do today and run it through the beam and make sure that your intrusion system is really ready and able to do its thing. Things like that will maybe help convince people that you really can do this safely. Okay, for beam safety considerations, first, operate in a location with sparse potential interactions. Try to get a no-fly zone permit if you can. Avoid the migratory flyways. Locate the beamer well above pedestrians, for example. Beamers on rooftops, not right on the ground. Have a well-fenced and monitored and signed enclosure. And design the system with interruptions being normal. That means you've got to have energy storage or some alternate means, because your beam is probably going to want to be interrupted. And so if you take that into your system design in the beginning, you'll be a lot better off. And we need to educate the public. Things like, the power company puts out these ads which says, "Don't touch a down power line." The gas pipeline people signs say, "Don't dig here." And no texting while driving. They put those signs up on the freeway. So we need to get a similar statement of some effect like that for the wireless power. Okay, so dim, divert, and douse. Here we go. Here's our beamer putting up this power beam into some object. And along comes some bats. Are we going to not fry bats? They're mammals. It may be a problem, but hey, we got to detect them. So you got to have some kind of detector. This shows eyeballs on here, but you may want something better than that. So let's put in the TVs and optical detection. You could also do it sonically with sound. And if something really big comes in, that's whenever you really got to do something. And you should have detected him by having a radar scanning around for an aircraft or tie into the FAA's air control system data. Or what happens if you have to do something? You can dim your beam. You know, it may be that your system can stand half power, and that may be, it's safe for some object. You can divert your beam. You know, if you're going to have a beamer that scans, scan it away from the potential intrusion. Or if worse comes to worse, you douse it. Okay, I won't go through that. We went through that. This, I'll have to say, when I was at the University of Texas as a grad student, I participated in getting a lot of this data. The Air Force wanted to know how much attenuation they could expect from airplanes high in the sky to the ground. They didn't want people intercepting their communications. So we had this long 6 1/8 inch diameter Proudlin coax, 100 meters long, into which we would put different gases, oxygen, sulfur dioxide, carbon dioxide, you name it, and run tests with these Raytheon tubes that had a guaranteed life, John, of 25 hours. So we had to set up our experiment, practice it several times, and we would finally then run it and try to get as few hours on that plystron as we could. Okay, so there are some attenuations there. That's good and that's bad. In some cases, you may also want to be able to use some of the really higher frequencies because they have a lot of attenuation if you don't want your beam to go very far. And so the atmosphere will help you do that. But otherwise, there are still some short wavelength frequencies that will make things smaller that have a small amount of atmospheric attenuation. They're just atmosphere gases. Now, rain, obviously, is a problem. But there's a lot of things you don't want to work in the rain, and that may be okay. So think about some of the higher frequencies. Okay, so the proposed stepping stones for wireless power. Aircraft launching and landing. Okay. RATO and JTO, think of wireless power transmission to assist keeping some of the weight on the ground. Airship wireless power to delivery drones. Downlinks. Okay, we'll show you a little later. I've been approached by some people who want to be able to beam power from a submarine to a high altitude observation platform. I mentioned the spacecraft and aircraft assisted launching. Oh, I'd really love for them to do something to get that Goodyear blimp noise off of the Golf Channel. Although I have some Goodyear stock, but yeah. Okay, and here's another very interesting point. 90% of the U.S. customers within 10 miles of a Walmart. Think about that. What does Walmart need wireless power for? Yeah, delivery drones. Okay. All right, now NASA is working on electric-powered aircraft. Electricity is great. You can deliver electricity without wires. And when I look at this plan form for this air vehicle here, I see a big round rectenna location on that sucker. You know, you could put lots of rectenna up there and beam power to it. Okay, then this is from the Forbes recent magazine, collection of flying cars. Okay, when are we going to get flying cars? Well, our own Aerospace America has a wonderful article on why this guy thinks personal aircraft is not going to happen. Okay, he has his theory based upon physics that when you look at things like insects and bats, birds and so forth, and things that people fly in now, something as your personal air car is never going to work because it can't hold enough fuel. Because most of the weight of getting these air cars off the ground is propulsion to lift it. Whoa, can we provide some power to these to lift it? You step inside your microwave oven, Faraday shield, close the door, turn on the power on the ground, and have get it up in the air, improving its payload fraction. And I look at this vehicle with this nice round circular planform holding up its propeller. What a great place to put a wire antenna to get power to it. Okay, and then, here we go. On the left is the Amazon Airborne Fulfillment Center. Airship up here. Drones or other air vehicles coming, bringing stuff up, delivering stuff. Gee, if you put a little wireless power transmitter up here and provided some power to these vehicles, you could increase their payload fraction. They don't have to carry as much fuel. And over on the right is the Walmart. Now this one they said designed to run at about 1,000 feet altitude. This is 45,000 feet altitude. But I think either one of them could probably use some help. So, John, I hope I've given you some stepping stones to try to get power up. Okay.
Thank you.
Thank you.
Any questions? Have you taken this up with Jeff Bezos yet? As an option for his
I'm hoping
new...
the word will spread.
Oh, okay.
You know, this just occurred recently here.
I like it.
All right.
It just looks like a patent diagram.
So just curious, somewhat of a new comment to this. You put up ideas for safety systems going back to '78. So what is the current status of any work that is being done on that, creating safety standards and systems?
None that I'm aware of.
Nothing?
I know no organized group that has that as their responsibility. Thank you very much.
Okay. Thank you.
Wait, do you have the...
Yes.
We should definitely catch up later on a couple of them.
I will mention for those of you who may not have been in the room yesterday for our first session that we do have a sign-up sheet, which I think Joe Rauscher is the keeper of. Gary Barnhart may have taken it from Joe, but Gary's going to be giving it back to Joe. So if you would like to get an email later with a site where you can download the presentations that are made during this event, or for additional information, please do sign up on the sign-up sheet. Joe Rauscher over there in the blue jumpsuit has the sign-up sheet. Do you have it yet? Okay. Very good.
Oh, and John mentioned if they're interested in being on the team of the...
Oh yes. So, and we also had a discussion yesterday about the current International Academy of Astronautics study group, and if you are interested in being involved in that study, please put an asterisk or a star of some kind next to your name, and you will be added to the roster. I don't know. I don't know how many of you are familiar with. Okay, Gary, is there some way to connect this computer to the internet?
Yes, it actually should be live.
Okay. It's an interesting concept. It's not true.
It's not true. Okay.
I'm glad we're testing that this morning.
Now, it was tested yesterday.
I am not connected to a network.
stand up and do aerobics and do some.
It's too early in the day for aerobics. Okay, I'll go with this one. I'll go with this one. Just, okay, never mind. But,
I will solve the mystery.
okay, very good, thank you. Oh, also, one last logistical note for just a moment. I would like to ask if everyone who makes a presentation today to please make sure that I get a copy of the slides for the other participants.
Is there a deadline to get it to you?
Yes, anytime today is fine. So, Greg Marinac, there we go. Do what later? Yes. Okay. So I'd like to just say a couple of words of introduction about Greg Marinac. Greg is one of the best punsters that I know. Meaning he twists and tortures the English language to say things which are very amusing to himself and other people with a similar personality disorder. And he was for many years involved with the L5 Society and with the Space Studies Institute in Princeton. He was unfortunately not able to be with us today because he's actually down in Rio de Janeiro at another conference. And I have to say, if I had to choose between Rio and Los Angeles, it'd be a tough choice. So let me offer you first some remarks from Greg, and then some slides that he provided highlighting, in particular, the life and the legacy of Bill Brown. And I don't seem to have sound here, but that's all right. Second. This is on, unfortunately, on YouTube, so we're going to have to do the best we can with the audio. I apologize.
Bill not only saw the future, he invented, built, and demonstrated the technologies.
Let's start that over. Let's start that over. There.
The world is only now beginning to catch up with the vision of William C. Brown. Bill not only saw the future, he invented, built, and demonstrated the technologies that are key to the survival of our species and the exploration of space. Hello, I'm Greg Marinac. I had the privilege of working alongside Gerardo Leone, Bill Brown, and Peter Glaser, who shared the vision of an abundant, carbon-free space power future. While O'Neill and Glaser were the best-known advocates for space colonization and space power, it was Bill who proved the feasibility of wireless power transmission. Bill invented the rectenna, the rectifying antenna, that's extremely efficient at converting radio frequency energy into usable electric current. Bill flew the first microwave-powered helicopter in 1964 and later demonstrated aircraft that could station keep using information derived from the waveform of the power beam. He initiated the field of beam-to-energy air and space transportation, which he dubbed transportronics. These ideas are just now being considered for modern UAVs. In 1975, under Bill's direction, NASA and the Department of Energy famously beamed kilowatt-scale power across the Mojave Desert at Goldstone to demonstrate the feasibility of transporting space solar power to Earth. Bill was generous and tireless in his support of this work. When Japan offered the chance to fly the first power beaming experiment in space, Bill donated the design of a custom rectenna. With his help, the system was built in less than 6 months and became METS, Microwave Energy Transmission in Space, which was launched in 1993. Bill was also always supportive of education efforts. He once drove his wireless powered transmission demonstration rig from Massachusetts all the way to Huntsville, Alabama, in support of the International Space University. He and his wife Marge traveled to the Arctic Circle to assist the University of Alaska in their wireless transmission work. Bill was a delightful gentleman who had a terrific sense of humor. When our METS Space Rectenna project needed a project name, I suggested that we call it Project Pampers. When Bill said, what does Pampers have to do with antennas? He said 2 words, disposable dipoles. Nobody laughed louder. Thank you for the chance to let me join you in honoring this amazing man who devoted his entire career to the dream of opening space for all humanity and transmission.
For those of you who don't know Greg, another one of his accomplishments was to serve as the Chief Financial Officer of the X Prize Foundation when it was originally formed following the X Prize. And I've got to find a way to get back out of this. Come on, let me go. There it is. Okay, fine. Yeah, I want to get rid of all those tabs. Let me go. There we go. Okay. And just to show you the slides that that Greg sent along, Greg's suggestion was that I should try to put the slides on top of him while he was speaking, and show the slides sort of in sequence as he went along with his remembrance. And I thought that was really kind of inappropriate because Greg is a historic figure in his own right, and so I thought it would be more interesting to see him. But these are the slides. So for Bill Brown, from Greg, first the inventor of the Rectenna, first microwave-powered helicopter, and it became quite famous by its demonstration on the Walter Cronkite News Hour in this time frame. The beam riding helicopter, you can see these cones that Greg mentioned. They detected the incoming RF signal, and because the transmitting antenna was designed to taper the beam, so it was largely a Gaussian. Bill's apparatus, all analog. I mean, there's no digital chips back there. Would detect the power levels on the 4 corners and adjust through a control system the helicopter to stay on top of the beam. The aircraft, the Milax aircraft that Greg mentioned, and also the Shark, the test at Goldstone that Dick Dickinson and Bill Brown were instrumental in, and we'll be talking more about that a little bit later today. The International Space University with a demo of wireless power at Kyushu. If I remember correctly, this is the one that Dr. Li Ming attended ISU in the early 90s. I'm not 100% sure about that, but I think that's correct. The METS demonstration of microwave energy transfer in space. I confess, until hearing Greg's account, I never knew that Bill Brown was involved in the design of the Rectenna for this experiment, which looked at the effects of microwave power transmission at fairly decent power levels through the ionosphere for the first time. There's his Rectenna. And there's Bill in Huntsville, again at ISU, with Greg Marinac and his family. So, continue this celebration of the history of space solar power and wireless power transmission. Once I double check on who's next. Okay, very good. So we have with us another individual of great historical note. I don't suppose you have any slides. I think you're probably going to just offer observations. Next, I would like to introduce Hal Walker Jr., who is, I think, most notable recently for his work with his wife in education and in trying to found a NSS chapter in South Africa, as I recall.
Successfully announced today.
Congratulations. And I was delighted to learn last year when I met Hal at one of the planning events for this Congress that he worked with Peter Glaser back in the 1960s. So, Hal.
Thank you. John, before you go, do me a favor and put that in and get me started.
Oh, absolutely.
Otherwise, I'll get lost trying to do it.
Oh, no. I'm good with that.
Well, good afternoon while John's doing that. It's morning, afternoon. I just arrived from
still
South Africa night before last, so I'm still over there. Yeah. But good morning, and again, my name is Hal Walker. I've been involved in the sort of space business since the late 1950s. And of course, it's been a wonderful experience, and of course, to work with folk that had a great contribution to, offered a great contribution to that effort, always made me feel like I was important. So that's kind of the way I always thought about it. So for us that at that time was involved with energy, our interest was lasers. And of course, I worked with Ted Mayman, the inventor of the laser, in 1960. So we had an opportunity to see beam power, maybe up close, as we would call it, firsthand. And what we're going to talk about today is how Peter Glaser made the laser and ranging to the moon and those things possible through his leadership in developing the retroreflectors needed to be able to return the beam to the source. And that was, of course, quite a challenge for us, because as you might understand, we'd never been to the moon before. So when someone asked the question, if we get to the moon, what are we going to do when we get there? Do the old usual, plant the flag, salute, get on the plane, come home. No, we spent $30 billion to get there. That's not going to answer. That's the wrong answer. So a question was asked, well, wait a minute. Suppose we were able to get a more accurate measurement of the distance between the Earth and the moon with this newfound technology called lasers. Thank you.
And just right here, down,
Okay.
forward and back.
Thank you. Thank you.
Okay,
Thank you,
wonderful.
John. So, of course, I think a lot of people may not know, but there was only one interactive experiment conducted during the Apollo 11 landing. Everything else was by microwave and transmissions. We that operated the lunar laser ranging experiment had the, what would you call it nowadays, I suppose, the benefit that we were the first folk to actually operate an experiment in history after a human being had landed on the moon. So I want to just mention that, because I think sometimes folk ask, who are those people? Where are they? Well, many of us are still around. I don't know how many of us are still around, but I'm still here, so thank the Lord for that. But the job that, again, Peter did was so important to that discussion. What are we going to do when we get there? Let's find out a more accurate measurement of the true distance between the Earth and the moon using laser. Well, then that brought a few of us into the conversation like, well, if you had a laser, how big would it have to be to reach the moon and reflect enough energy back to make that ranging experiment? Well, you had to have a laser that was 300 times brighter than the sun. Yeah. You had to have a laser that didn't physically exist in that time, because we operated single pulse mode. giant pulse, as we used to call it in those days. So this is where I'm going to start this little talk from, is how Peter helped us to get that job done. And my job was to build that laser and operate it during the landing. Okay. Apollo 11. So this is how we all came to be together in this thing, Peter and us and other guys, is Apollo 11. Well, Apollo 11 has a great history, and everyone knows it, so I won't go into that point. But the thing about Apollo 11 that was so interesting is that the only thing carried aboard the ship, the lander, that was so important to us because we were ready to engage it, was the retroreflector. So of course, that brings us to this next scene, which is at Lick Observatory. Now, many of you probably have read stories about ranging experiments that have been conducted over the past 40-some years from McDonnell Observatory. So I chose to use one of their slides here in a moment to talk about how the physicality worked. But we were actually operating a scientific experiment from Lick with a giant pulse laser. This is the laser system right here, multi-stage Ruby laser, developed 1.5 gigawatts of power, single shot, took 40 seconds to charge the capacitors in it for one shot firing, and then you held your hands over your ears in case something blew, but this was an experiment. We had a few bangs along the way. But our purpose here to show this is that we had to integrate that laser into the Lick Observatory's telescope. Because, of course, the moon's flying by and we're flying the other way and so forth and so on. So how do you track all of that? Well, those guys were able to do that with their observatory technology. And there's the guy we was looking for. Roughly 24 inches square, had 100 elements in it. Of course, what was so critical to our success, as you may know from reading about this story, is that if a beam of light appeared in this direction and struck that reflector, it came directly back to the source. Sort of broke the law of physics that things get scattered and off in other directions. And of course, Peter and those guys that solved that problem made this experiment successful. So the laser was actually a nice, wonderful source for us, but without the retroreflector having that particular characteristic, we had no chance at all really to accomplish it except to get a bunch of what we will call erroneous and extrapolated returns. And so who would know what the distance to the moon was? Nobody. But by that, those devices having that ability to return the beam to the source actually gave us a chance to do this. And the next chart is going to show us how that worked. Well, here we are at Lick Observatory. There's Neil Armstrong and Buzz on the surface. And there's that retroreflector that we're talking about there. And of course, since I fired the laser to the moon, guess what? They gave me one. So there it is. So I'll have that around if you want to see what one of those retroreflectors look like. But you can see some of the characteristics of the performance that we had to deal with there, of course. And one of the things that was mentioned with beam powering, you got to look out for other folks. Well, guess what? Lick Observatory is just above San Jose and outside of San Francisco. You fire a 1.5 gigawatt laser through the atmosphere there. Folk like airplane pilots, think about it. They got laws against a light, like a little laser. Now think what it looked like 1.5 went by. So we had to be sure that we could control airspace around Lick Observatory with a very safely system, which we brought the National Guard in. There's the military to help us. So they had radar systems around the area, scanning, and had remote control to us before we could fire our lasers. We had to get a control signal from them that the airspace was clear. Now, one of the things I'll do quickly just to describe this, folk ask me, when you take 1.5 gigawatts and 10 point something joules of energy, and throw it to the moon, what does that look like? It looks like taking a barrel of water and throwing it, striking the moon, having the light bounce off and all over the place, but certain amounts of it come back at you. And of course, this is what this illustrates, going in that direction and coming back. But when the energy returned, it was only 5 photons. So we had one of the most sensitive receivers at that time in the world. Well, an interesting thing happened. We had an accident happen. You always have accidents when things are great going on. You ever experienced that when things are going just wonderful, an accident happens? We ended up blowing up the 5 photon detector at MIT. It took 10 years or something to build for us. But anyway, so myself and a great guy, Irv Weiner, we went to the observatory's management and asked them could they help us with a photon counter that they might have that we could modify. So we did, and we actually turned that counter into something that was able to get returns back for us over the next few weeks. And of course, one of the things we found out there is we reduced the error at that time of the known distance between the Earth and the Moon from 200 meters to 6 inches. This was the outcome of that experiment. A little bit about, see, my wife just walked in. A little bit about our program, AMAN. I just mentioned that today was our first day as a National Space Society chapter from the country of South Africa. Well, here we are back in South Africa, back in the day. And of course, the reason we were there is President Mandela. You know, these folks, these names and people are so important to us. They get into your life and things. Just like Peter. Peter involved in our changed our lives. Without him, we wouldn't have been able to range for the moon, or without his team. Without President Mandela, we wouldn't have been able to have the recognition today of the first ever in history National Space Society chapter on the continent of Africa. Is that worth some? Was that worth a hand? Names mean something.